presentation. Really cool.
Yeah. Thank me once I'm done presenting. We'll, we'll see. Okay, so I think, how do I present? I'm recording now, hopefully. Share screen. Oh, there we go. Cool. How's that? Can you see it?
Yeah, perfect.
Awesome. Okay, so, oh, you guys can see all your faces. Is that okay? Okay, so today I'm presenting on improving data-driven global weather prediction using deep convolutional neural networks on a cubed sphere. So as a kind of introduction to the problem, currently most state-of-the-art weather prediction is done with physics-based models. So you insert like the initial parameters, like, here's where the clouds are, here's what the temperatures are worldwide, here's what they were like, 30 days in the past, and then physics model takes over and helps you predicts things in the future. So far that's like the most state-of-the-art. Data-driven methods have not overtaken it yet. They haven't come really close. But as with everything else with deep learning, we're getting loads more data. GPUs are becoming a thing. So we think that data-driven, machine learning, deep learning specifically, will eventually overtake the physics-based models. So to give an example of like what kind of weather stuff we'd be predicting, in this case here on the right, I'm showing precipitation going on over the course of a few days. So some previous work so I kind of like to describe, I kind of like to put myself into the author's shoes. Like, what were they thinking? How did they like come up with this paper? Like, where did they start? So in this case, it looks like they started by finding this one paper by Wayne et al. That used UNet to try and forecast geopotential height in the northern hemisphere. So full disclosure, I don't fully understand what this means, but I know it has something strongly to do with like how clouds move. It determines how clouds move and pressure systems. Very useful for weather. So in this work, they were able to create good forecasts for up to 3 days. They were capable of predicting 14 days, but results were kind of mixed, not that great. But 3 days, they were very good. So to give an idea of like how they trained it, they used weather data from 1979 to 2010, and they had a new like frame, a new like data input for every 6 hours, and they had a fairly high resolution latitude longitude grid. Yeah, and like I said, it did not outperform physics-based models. So in this paper, they started from that and tried to scout out weaknesses so that they could try and like find different ways to improve upon their work. So number one, they identified that the model of the previous paper had a kind of poor representation. So in this work, the previous works, it would only it only predicted in the northern hemisphere, and it used a kind of representation similar to what I show on the right here. So this is like the kind of representation of the globe that we're all kind of used to seeing, but it's a bit misleading. So for instance, like this point, if you're looking at the Arctic, or if you're looking at like 90 degrees north or 90 degrees south, it's not immediately obvious that if you move 1 pixel down from here, you'll end up over here. So it has a couple like problems with it. It is kind of distorted when compared to like an actual globe. So another problem that they recognized was that the previous model was unable to accurately predict in the long term. So its predictions were kind of unstable. So in their models, in both models, in both cases, in the previous paper and this paper, the model is input some amount of data and it outputs some data, and that's your initial prediction. If you want to go further into the future, you take that output, feed it back into the input, and get a new output. So you can continuously go into the future with that. But as I said in the previous work, it's kind of unstable. So their goal was to kind of attack these two problems. So the first problem, one of poor representation, like I said, if you're trying to represent a sphere on a 2D plane, it can get a little messy. It can get distorted. And this is kind of they realized in the paper that this is sort of similar to 360-degree vision problems. So some cases, I mean, this projection up here looks, the first one looks pretty nice, but it has its own series of problems. So they decided to like kind of borrow this concept of this cube map projection and apply this to, you know, their problem, the weather problem. So here's kind of like showing that projection in action. So if we're using a 2D convolutional neural network, you know, we've converted this into a 2D space, but we give it a couple like conditions, I guess. So what's I saying? So as opposed to like the previous one where there was like kind of a singularity if you went too far north, this one it's kind of it's very clear what you do on the edge cases. So if you get too high at this point, you just borrow from the adjacent space. So that's kind of what they're showing here. Also worth noting is that the maps for like the north and south poles they share parameters, whereas the ones around the equator do they also share parameters, but they're separate. I'm not phrasing this well. The north and south pole use the same parameters as do the ones around the equator. And the second problem is the one I mentioned, unstable long-term predictions. So ordinarily what you do in order to train these kind of predictive models is you train it to reduce loss for a single iteration. So you input the weather at time is equal to 0, and you get an output at time is equal to 1. And you minimize the error between the predicted time is equal to 1 and the actual time is equal to 1. So what they did in order to try and stabilize this is, instead of just doing that one-time step, they took that one-time step and then fed it back into the input and got another output at time is equal to 2 and added that to the loss function. So you could do this for like however many time steps you want, but they found that setting it just to 2 time steps was pretty much all they needed. And here's a better illustration of what is happening. Yeah. Okay, so for the model architecture they used, like with the previous one, they used a U-Net architecture. So if anyone is unfamiliar with U-Net, what this is effectively doing is it's kind of like an autoencoder. So you take all the inputs at a very high resolution, and then you kind of compress it into a small like representation. So this representation down here will give you kind of the bulk of the information. And then once you've got it down to there, you start blowing it back up. And the previous layers will give it they'll gradually give it, or they'll incrementally give it the finer details of that were observed in the inputs. And eventually you get, something of the same dimensions as your input, as your output. So specifically, here's the main architecture. This is mostly here for reference, but it's a fairly standard UNet. There's nothing particularly special about it. So the data set, I didn't fully understand most of all of the stuff about the data set. Yeah, it's kind of a little sloppy here, but but it's an open source data set. It contains a bunch of different possible a bunch of different weather data, such as surface temperature was one. There was a couple different atmospheric pressure things that I mentioned before. I can't remember the name of it. I apparently didn't add it here. But what was I saying? Oh, but it's at a 3-hour resolution. So some of the benchmarks they used to show how well their model performed, they compared it to number one, the actual data itself. Number two, persistence. So persistence, all it is saying it takes the very last input that you were given and uses that to predict the future. So this is kind of a good baseline to see if your model is actually working or not. And the last three here are varying levels of actual physics-based models. So the smallest one here is the T42 model. And I think this one down here is the state of the art, or at least considered state of the art.
Can I ask something there?
Sure.
I'm think I understand, but I'm not fully sure. Persistence, does persistence mean that basically they assume that the temperature or the pressure, air pressure, does not change at all? It just stays constant? Or?
Yes, exactly. So if you're doing a daily forecast, persistence is just taking today's a temperature forecast and predicting that for the next 7 days.
Never changes. All right. And the climatological value, that's basically a value that's defined for every day in the year, right?
Yep.
So for the 365 values.
Yep. So this first one is assuming perfect prediction, I guess.
Okay.
Or I think or daily. Yeah, it's a kind of smoothed out perfect prediction.
Yeah.
Daily, daily means. But yeah, I kind of ran out of time, and yeah, since this isn't for a grade and my boss isn't ragging on me for this one, sorry guys, I didn't finish the slides, but the main points, the main results from this paper are that the deep learning models still don't perform better than the best neural weather prediction models or the physics-based models, but they did perform better than the weakest one that was tried here. But they are much faster than standard physics-based models. Physics-based models, you'll need loads of computational time, whereas these were done in minutes. So yeah, still work to be done, but very promising, a very promising direction. So yeah, that's about it.
All right. Thanks.
Yeah.
Thanks for the presentation. I think it was
really thank you very much. Yeah. Actually made some points more clear than when I was reading the paper.
Yeah, so they talk about the 500 geopotential height thing.
Mm-hmm.
I think that means basically the it means, I think it means the height at which the air pressure is like 500 hectopascal or something like that, right?
I got that impression, but when I like looked up the Wikipedia for it, it was measured in meters squared per second squared. It just,
Okay.
it's not, yeah, it didn't really click with me. I don't fully understand it.
Yeah.
But yes, from what I've read, your description sounds correct. The height at which the air pressure is 500 kilopascals or whatever it was.
So are there still things that any of you don't understand about the paper, presentation, or any concepts?
So I was just wondering about this multi-step loss function, because it's the first time that I've seen that. If that's like a common thing that you do that in problems that predict time series, or if it's just uncommon thing, or I just never stumbled upon it.
I had never stumbled upon it, and this was, to me, one of the most interesting parts of the paper. Well, not interesting, but like for at least my work, something that could be immediately applied to what I'm doing. And so simple, I just didn't know it existed. Yeah, so I don't know if it's common or not, but this to me was the first time I've seen it. And their code was like, what is it? It was like 10 lines of code to implement this new loss. I didn't realize it was like possible to do that in Keras.
Yeah. Well, it's basically just like where normally the input would be you have the width, height, and the depth of an image, where the depth is well, width, height, and depth. That represents one time step, and here they just concatenate a second time step, right, as the input. So they just make the input twice as large, and the output as well. But they could have also solved it differently, right? So they could have just used one time step, pass it through the UNet, and then use that as the next input for the UNet, right?
Yeah, I think
I'd be less efficient though.
Yeah. But yeah, it's like super neat, simple, and like very like almost if you're doing any kind of forecasting, a next frame prediction for like autonomous cars or something like that. This, or, weather prediction, stock market prediction. This seems like applicable to like anything.
Yeah.
So it's like
I think that it kind of makes sense, right? When you think about it, like you're testing your model and it's so simple. I also, as Julia mentioned, I hadn't seen that before, but it totally made sense, right? That you are going to be correcting the model with, one step forward. But I'm just on what would the prediction be, right? Instead of just doing it with the immediate one after, like of the result of the current variables. What I am curious about is why did they decide to use correction, like to use two steps, right? To do two consecutive iterations as that. Like as Eric mentioned, they found that the optimal kind of range for it to correct the model was 2. That's the part that I'm curious about. Why 2? How did they define that, and not 3 or further?
Yeah, to me it looked like they did it mostly out of computational efficiency. They could have gone higher, and I suspect they probably would have gotten better accuracy, but they seemed very concerned about reducing the computational time and just making things faster. Like there was a section in the paper where they listed like there were like half a dozen methods. It was like, yeah, we could have done this to make it better.
Yeah.
But it seemed like a lot of work.
That typical problem, no?
Yeah. Yeah, I forget.
Yeah, I was thinking that. Yeah. I was thinking that perhaps it was that if you are going through a range, for example, of 3 iterations, that perhaps the model is having a harder time to understand on which part of the range kind of this it is attributing the diversions, you know, to the actual one. But I don't know what you guys think. So I thought maybe that's why they cannot go further and further, because the model is having a harder time to understand like where to do the adjustments. I don't know.
Yeah. Yeah. I wonder if there's like
Yeah.
an overfitting thing that they could come across with doing too many time steps or something. I'm not sure.
I think indeed that the main takeaway of this paper is that they want it to be fast, so they try to reduce the computational load. And with adding more time steps, their main goal was to make it more stable, I think, in the long term. Like long-term predictions, they want to make it stable and not diverge the outcome to model. And I think they showed in the results that they can predict like a year in advance and it doesn't diverge at all. So they basically achieved their goal in that, I think. So it was just enough, I guess.
I think I somehow also read something in the paper that if you make the T, like the big T too big with the multi-step loss function, then they said it would be too smooth and only focus on like the large scale changes.
Oh, I missed that. Where is that?
I don't know. I just wrote it on my piece of paper when I read the paper, so I don't really know where I saw it, but it was somewhere in the paper. I can look.
But yeah, it's page 7. Max says. Page 7.
Oh, yep, I see it. Oh yeah, okay. So they want more precise, like concrete predictions, and that would kind of make things smooth, just generals. Yeah, I see.
But maybe they could also tweak the alpha so that you decrease the alpha value for time steps that are like further down the road or so. Then
yeah, that makes sense.
Yeah, that makes sense.
And that's also why they evaluated their model with 2 metrics, right? They used the mean squared error, but also a metric that basically determines how much you don't follow the average, or you can capture anomalies. I actually didn't really intuitively understand that metric. Does any of you do? Understand the second metric, the ACC?
The what?
Like they define 2 metrics, I think, the mean squared error and the ACC. I think the anomaly.
Oh, that's right.
Coefficient something.
Yeah, I didn't fully understand it, but they gave a kind of summary of what it is indicating. Where'd it go?
Yeah.
Yeah, perfect score.
I think
perfect forecast has an ACC score of 1, while a score of 0 indicates a forecast with no scale relative to climatology. Where the squared error penalizes a large difference in actual forecast state, the ACC penalizes incorrect patterns of anomalies and is agnostic to the magnitude of the anomalies. So it punishes like major mistakes as opposed to oh, you predicted clouds here, but it wasn't cloudy enough kind of thing, it looks like.
Yeah. I think that the main point is that if you would have a model that would basically only predict the climatological value, so basically only predict the average value, then that doesn't really provide any information. So your model is good on average, but it's not good in any extreme cases.
Yeah.
I think that's what they try to capture with that metric.
Yeah, that makes sense. We don't want to know if it's cloudy and cloudy over the mountains in the fall or something like that. We want more precise, more dynamic
Yeah.
behavior. Yeah, that makes sense. I forget. I have some other question.
I have one question about figure 3 in the paper. I don't know if you have that in front of you. There they show the results of the different models. So they on the left, I think, on the left they show the mean squared error, and on the right they show the different metrics, so the ACC metric. What surprises me there is that all models, so if you, for example, look at figure 3A, so top left, all models start at the lower error rate than the climatology benchmark. So they're all better than climatology. But at some point, after a few days, they become worse than climatology. And I wondered if that actually makes sense. Like,
I'm wondering
why would the model be at least as good as climatology?
I'm wondering if I have the wrong figure. Oh, whoops. Okay.
Yeah,
I have a different version of the paper. That's why.
That's the figure I'm talking about. Yeah.
Oh, you can see this.
So
Okay.
yeah.
Yeah. Whoops.
So figure 3A.
Mhm.
You see the error rate, so lower is better. And on the x-axis, you see the forecast day, so how far along in the future you're predicting. And you see different lines where blue, I think blue is the
This model.
most method, yeah. And the brown dotted line is climatology. So that's basically a constant value, a constant error rate. And I was wondering whether it makes sense that the blue line starts below the brown line at first, so it's better than climatology. But at some point, it becomes worse than that. And that it's the same for all models. Shouldn't like all models be at least as good as climatology and maybe improve on that?
Yeah, that does seem odd. Yeah, you would think instead of being asymptotic to whatever this is, it would start curving. Yeah, come to converge with climatology. That is weird. Well,
I would at least expect the other benchmarks like the IFS and the S2S to be better than that. Because like this model didn't have the time of year as input. If it did, it might have learned like the climatology value as a bias. But I would expect the other models would have that information.
yeah.
I don't know.
So I'm having a hard time with these graphs anyway.
That is like a really good point though. Yeah. So we know this is like the global. So just to like I guess re-explain. So persistence here is if you predict, it's like okay, today's forecast is going to be the same. Well, the weather next week is going to be the exact same as it is right now today. That's what persistence is predicting. So everything is going to be better than persistence, no matter what. Climatology is like the average year round. Yeah, so you would think it would start converging, like the predictions would start converging on the year round average, unless I just misunderstand what climatology actually is.
Yeah. Maybe I'm misunderstanding as well.
Yeah, I'm gonna have to ask some of my colleagues about this.
Yeah.
I'm technically I don't know. I tell people I'm a weatherman, but I have no idea about anything meteorological. Yeah, but I work with like 3 meteorologists, so I'm gonna ask them about this.
All right. Well,
That's interesting.
I'm interested to hear about that if you have an answer.
Yeah, I'll post that on the Slack if I come up with something.
Yeah, I am also having a hard time really like super making sure that I am fully understanding the graphs, right? But given that it has a constant value, the climatology one, I would say that perhaps it is the measure of the deviation itself. It is already dependent on the climatology values. You know that it's kind of, sorry, we're using a microwave here. That given that, if I am not misunderstanding, climatology has a standard value. It's the brown dotted line, right?
Mhm.
So, and when we look at the calculations of the ACC, we do know that the value of C, it explains, is the climatological value for the verification time, which is the climatological values used. So I don't know if it is that the measurement of the error by itself, it's holding, climatology. I'm just like speculating here. I don't know, but that might be something like that, because you see, it's just assuming that the error stands throughout. That tells us that it's the same value. That tells us that it's kind of the base of it's inside. It's the base for the benchmark or within the error calculation unit, I would say.
Yeah, but you're not in particularly talking about the ACC metric, right?
Yes, in the set on the like in the set in the figure A 3.8, right? So that's the one that we are talking about, no?
Yeah, 3A, the top left.
Yeah, and climatology, it has a constant value of 800.
Yeah.
So it says that Seth, who is yeah, the error, right? The error rate is it's constant. So I don't know. I just get that by the way that it is calculated, it is using as a base climatology, and that's why it has like a predefined constant value of 800. I don't know.
Yeah.
I don't know if I'm super mistaken, guys, and if I'm confused, like please say yes and continue. But there's a point of it being a constant value on the calculation, for example, of the ACC. That's why you have that it is 0, because on the formula of the ACC, it's itself like it's included there as C.
Yeah.
So
So
it is just
this is part of the ACC metric. So
yeah. So,
ACC metric is basically a metric for how much you deviate from the climatology. So climatology does not deviate from climatology, of course.
so
So that's
yeah. So it would be about understanding of why, what's the relationship with this within the RMSE, as to see on which degree is it just inherent to to climatology, you know. I don't know, like might need more detail within the calculation of RMSE.
Yeah. I think it's 800 because like the climatology is, I think, based on the data points they have from 1979 to 2000 and I don't know 10, something like that.
Mm-hmm.
So I think they just calculated the average for, let's say, the temperature. They calculated the average temperature for each day of the year. So January the 1st and January the 2nd and so on. So then you have 365 values. And I think what they then did is they ran over all days from January 1st, 1979 to December 31st of 2010.
And then,
And then calculated the difference between the actual temperature of the day and the climatological value, and they average that, and I think that just comes down to 800. If that makes sense. That's how I interpreted it.
yeah, like I understand by the definition of the formula, like that's what it says, right? Like it's basically the square root of the square of the difference between the forecasted and the forecasted value and observed state. I just think that it's funny that that it is a constant value, right? Why
Yeah,
is it always
there's-
800?
Yeah, there's something up with that. Yeah, I'm still missing it. The fact that it's constant probably means it's not like an average. I don't know what that means. What could be constant across all days?
I don't think it's constant across all days, but I think it's constant when you average it over all days. Because on the x-axis you see 1 to 14, so that's the forecast days. But these lines are averaged over.
Yeah, makes sense. No, yeah, I get you now. Like you cannot, given that the data set is many years, you cannot just pick a sample of 14 consecutive days and be checking that. Eventually, you would just have to assume a constant error level, right? Yeah, it makes sense. Still, we can, like, I'm just now curious about seeing if I can find maybe, like, online. We can Google a bit, try to take a dive and find any more details about the calculation of the RMSE.
Yeah, all the code for this is online somewhere. I found it previously. In the paper, there it is.
Okay.
There's the GitHub code.
Yeah, it's really neat that we can try this ourselves, basically.
Yeah.
For us deep learning folks to be able to do this.
Yeah, and they got like a nice little tutorial thing here. I don't know, the third tutorial here was like the important one. Where'd it go? And here's the special like line of code that it does the predicting sequential what do you call it? Sequential outputs, and does the error, computes the loss for each step. Yeah.
All right.
Anyhow, I'm not an expert in this, but I've looked at this code a little bit, enough to tell my boss, like, hey boss, I want to work on this. Can I do this? Like, yeah, okay. Later.
Right. Are there any points any of you have questions about? Or want to say something about?
I have just one like general question. Would it make sense to also try a different model, or is UNet pretty much the gold standard that you can do here?
As far as I know, UNet is at the moment like state of the art. Well, not close to state of the art anyway. At least in terms of neural networks, yes, state of the art. There's been a couple like publications from like Google and whatnot that seem to use like I think it was like just last year or fairly recently. Google was doing like precipitation prediction, and they used the UNet as well. So it is kind of the standard right now. But I think that there's a better way to do it. I'm still brainstorming ideas, but I think there's something out there better than UNet. But if you can think of anything, I'm all ears.
No, this was just a wild question. I'm sorry.
Help me get a raise at work.
No, Julia, now the pressure's on you. Maybe That can be the next presentation. What should be the architecture that we should use now instead of UNet for this? We believe in you.
Oh no.
You can do it.
Like the whole, I don't know, something about UNet kind of it's clearly useful for this problem, but something about it still irks me. So like in this case, we're predicting kind of sequential time steps, time step 1 and then predict time step 2 kind of thing. But so like I what's the word? I can't think of the words. Oh, words are failing me. What's the word for like when you're trying to calculate how far a neural network is like influenced like by pixel? So like if you have like a 1-layer neural network that has a 3x3 kernel, it has pixels are only affected by like pixels.
Oh,
like
the
3 pixels.
receptive field?
Sorry?
Receptive field, is that what you mean?
I
The
think
receptive field?
yes, the receptive field. So like here, I don't know if the receptive field is all that large.
Yeah.
It's only like, I don't know, like 5, at least coming down to here, it's like 5 layers deep or something like that. So something in Antarctica actually influencing something in North America if the perceptive or receptive field is only like so deep. I think there might be a better way of like representing that, showing that
Yeah, when
the
I saw this,
predictions
sorry. When I saw this schematic, I thought that was fairly shallow, small network, I think, actually, for this task. I think it's a pretty complicated, complex task. And UNet, I think, I'm not sure actually, but I think it's not actually state of the art at the moment. It's more like a standard baseline model, I guess.
Yeah.
But
yeah.
I'm not sure. I wouldn't be able to name a better model for this task. So I'm
Yeah.
not sure.
For like a precipitation task or something like that, I was kind of toying with the idea of how do I put this? So like if you're familiar with like some facial recognition task, they kind of break it into like 2 different representations. One is the facial structure, or one encoding. I don't know how to phrase this better. For some facial recognition problems, they break it into 2 tasks. They kind of represent the face in like 2 different embeddings. One has like the actual facial structure and features of somebody's face, and the other has the orientation. So which way are they looking? Where are their eyes looking? So I was thinking about somehow breaking a problem like this into something like that. So it has multiple. I forget what this like bottom layer is called. I guess embeddings. So like
Bottleneck.
yes, bottlenecks, multiple bottlenecks. So one might have one might be like an actual estimation of where the clouds are going to be, and another one might have like an estimation of how sticky or like clumpy, how willing the clouds are to stick together, or how unpredictable they are. Like, so putting these into 2 representations, I don't know if that'll be beneficial or not, but
Yeah, I mean, in theory, the bottleneck you see in the middle, like at the bottom, it has separate channels, right? I think it has 128 channels, I think. So in theory, every channel could represent something different, right? So one channel
true, yeah.
could represent the temperature, one could represent the pressure, one could represent the clouds or something like that, I guess.
Yeah, I'm not describing my idea too great, but
No.
yeah, that's
Well, it kind of sounded a little bit like attention from the language models that look to different things.
Yeah, that's another way of like definitely improving this anyway. Just apply attention to anything and it automatically seems to do better.
So you make it into a transformer and then everything's fine.
Yeah, there's
Well, if you're willing to publish a paper very soon, there's a way to go. Just redo this with transformers and
Yeah.
you're done.
Hey, look, I beat the second, physics-based model. That would be nice.
But I think this paper, if I'm understanding right, it's a very recent paper, but it looks to me like they just want to basically establish a baseline. Like, I think.
Yeah. Yeah,
Which on which others and they themselves can improve upon, hopefully.
Yeah. They stepped up from like the previous. I don't even know if the last one they'd consider it a baseline, but yeah, definitely just one-upping the previous authors. Like, see,
Yeah.
look, we did it better, guys. Top that.
Yeah, but I wonder whether there's actually much research in this field where they apply deep learning to climatology. I don't know.
There definitely
looks-
is, but it hasn't really blown up yet. It seems it's all kind of on the fringe, on the edges. Everyone's like waiting until like that next big breakthrough and like, look, we just beat the physics-based models, and then everyone's going to jump on it, I think.
Yeah, exactly. All right. Just so you know, Max also posted something about climatology. If
Oh, did I miss
I
a
think-
message?
when we were talking about the figure 3a, I think he posted that. I mean, in Zoom.
Chat.
All
I
right.
don't see it yet. Is it in like the chat somewhere? I'm not seeing it.
Oh yeah, sorry, in the Zoom chat.
Oh. I'm not sure how to see it. Oh well.
Maybe
what-
Max, we can just put it on send it through Slack.
Oh, I found it. Okay.
Yeah, it's on a daily basis.
Interesting. Still seems weird that it was like constant even on a daily basis. Well, maybe not. I don't know. Is it?
I think it made sense, Chris's kind of understanding of it about how, you do have to establish, or you do have to establish an average or a representative value of the error for any day or any consecutive group of days. So that might have been it. Like, it makes sense.
I will see after this meeting if I can come up with a toy example of how you come up at as a constant value. I'll see
Okay.
if I can.
You can present it right after Julia presents her new architecture proposal. We're already building the new meeting.
Yeah, who knows? All right. Well, are there any questions, or should we conclude it at that? No?
Any recommendations for the next paper we should read? Anyone have any?
Recommendations? Yeah, actually, yeah. Does any of you have any recommendations? Indeed. the latest paper I was reading is CenterNet. I don't know if you've heard of that. It's basically object detection network where they well, I'm not sure if you're familiar with object detection, but there they, no, it's not that one. Objects as point, actually. The second one, objects as points. It's object detection where they detect the center point of each object, and for that center point, they then also predict what the width and height is of that point and what class it is. I thought it was pretty interesting.
Good.
Yeah, we can take a look at it.
Yeah.
Like, yeah, I don't know, Chris, what do you have in mind, like to choose the next one? I like this, like, I haven't read it. I like always the topic of object detection and image processing. We can open on Slack to see if anyone else has something else, maybe a poll to vote over there. Also, Max is sending a suggestion on chat related to robotics.
Yeah, so, sorry, what's your name actually? JP Montana?
Yeah. It's Juan Pablo, actually, but everyone calls me JP. I live in Norway, so there's not a lot of people that say Juan Pablo in here. So JP is quite okay.
No big deal. Right, I think I call you JP then as well. So what was your suggestion?
If we can open a poll in the case that we want to just have some time to see if anyone wants to screen their papers or has any other ideas. I already like the object detection one that you suggested. Like, it sounds like a very interesting topic. So yeah, if not, we can also consider that.
Yeah. So do you mean that we post some proposals for papers and just hope that anyone is willing to volunteer and present one of those papers? Or
yeah, we can do it like that. I think, for example, like honestly, it was very relieving to see how this session went. I really like Eric's presentation because, I read the paper and I ended up with questions that I ended up checking myself and everything. But it's very good to see that, to have a mirror to be bouncing this with, So I think that based on this, I also feel like it's only about presenting your understanding, right? So it opens more to anyone can present in a way,
No,
in a few words, I was worried about I would not volunteer unless I was super sure that I could present and I was super confident about all the processing. But it's very good to see that we all kind of can try to understand it together, right?
Yeah. Yeah, no,
I think so too.
So we can, for example, propose this and say, okay, here's a list of maybe here's one paper already, if any other one has any other ideas, and if anyone volunteers. And if no one volunteers, I think we'll figure it out. Like, I'm willing to take a dive if really there's no one that volunteer. But I'm confident that the likelihood that someone's field of expertise is a little bit more related to object detection, for example, would volunteer, perhaps.
Yeah, yeah, that sounds good. All right, let's do that then. If Max doesn't do it, I'll also add his paper to Slack.
Sure, and maybe also something about language models at some point. I would propose the same solution if someone volunteers that is like an expert in that, then I will gladly hand over the topic to the person.
Right. Yeah, sounds good. All right. I think we should thank Eric for the presentation. It was really well. Thanks for that.
Well, thank you for not roasting me for being semi-unprepared.
No, Eric, it was very good. Thanks for thanks for holding the pressure, right? For being able to stand the pressure of being the first one. Good job.
Sure, and really you clarified the paper a lot more for me.
Awesome. I'm glad to hear that.
All right. Thanks for joining all. And I'll see you in about 2 weeks then, I think. What?
Sounds good.
Okay.
Yeah.
All right.
Nice to meet you guys.
Bye-bye.
Bye.
Bye.